In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about gravitational Poissonian spontaneous localization model of hybrid quantum classical Newtonian gravity, energy increase, and experimental bounds. It was written by Niccolo Picconi from the University of Trieste in Italy. The gravitational Poissonian spontaneous localization model is a hybrid classical quantum framework in which Newtonian gravity emerged from a stochastic collapse of a smeared mass density operator. Consistency of the hybrid dynamic entails momentum diffusion and hence spontaneous heating without smearing, which enters both the collapse measurement and gravitational feedback components of the dynamics. The heating rate would be divergent. Previous work assumed identical smearing for both components. Here, we treat the general case of distinct spatial smearing (GRCX and GRGX), characterized respectively by length scales (RC and RG. We characterize the spontaneous heating rate for arbitrary GRCX and GRGX and then discuss which smearing profiles minimizing the spontaneous heating rate in relevant physical situations. Remarkably, there are situations in which, while the measurement noise remains the same, allowing the GRG is not equal to GR6 may reduce the feedback-induced spontaneous heating by more than 60 orders of magnitude already for RG is equal to 10 RC. Finally, we use our results to estimate the spontaneous heating rate of neutron stars and to set new lower bounds on the model's parameters by comparing the theoretical predictions with astronomical data on temperature, radius, and mass of neutron stars. Now I want to go through the introduction. The most common approach to merge quantum mechanics and general relativity consists in quantizing the gravitational field, producing frameworks such as string theory and loop quantum gravity, among others. However, hybrid classical quantum theories of gravity in which space time remains classical while matter is quantized have recently emerged as serious alternatives rather than more semi-classical approximations. In fact, whether gravity must be quantized remains an open experimental question. Purpose tests could distinguish quantum, classical, and intermediate scenarios, but have not yet been performed. The central theory challenge for hybrid approach is consistency. The historical semi-classical gravity approach, in which classical gravity coupled to the expectation value of the quantized stress energy tensor, fails as a fundamental theory. Even in the Newtonian limit, the corresponding dynamic is nonlinear and allows for superluminal communication. This pathology can be avoided by introducing the stochasticity. Modern hybrid classical quantum theories rely on dynamics that can be seen as measurements plus feedback schemes, whereby constructions the reduced dynamics is linear at the density matrix level. However, stochasticity entails momentum diffusion. This manifests in general as a spontaneous heating rate that could in principle be large enough to conflict with observation. Reference 8, we investigated the hybrid classical quantum model of Newtonian gravity outlined in reference 21 and named in GPSL. A GPSL is actually the abbreviation of the gravitational Poissonian spontaneous localization. For gravitational Poissonian spontaneous localization, in summary, the GPS or gravitational Poissonian spontaneous localization model employs the collapse centers of the PSL model to source instantaneous gravitational pulses as depicted in Figure 1 on Large scales, this recovers the Newtonian phenomenology, the GPSL, the gravitational Poissonian spontaneous localization model, has a distinctive feature compared to other approaches such as the Taylor DOC model. In the absence of the matter, the Newtonian gravitational field vanishes exactly rather than fluctuating around a zero average. This property may be essential for consistent relativistic extension. In this paper, we address a question that is critical for the visibility for GPSL or gravitational Poissonian spontaneous localization, whether the predicted spontaneous heating is compatible with observational data, as in all other hybrid quantum classical models of Newtonian gravity. A smearing procedure of certain operators is needed to avoid a divergent heating rate. In GPSL or gravitational Poissonian spontaneous localization, the smearing is applied to the mass density operator, which is both the measured quantity and the quantity through which the gravitational feedback Hamiltonian acts. In reference 8, we assume this smearing to be the same for both the measurement and feedback channels. Here instead we allow them to be different and characterized by two different smearing length scales, RC for the measurement part and RG for the gravitational feedback part. We derive the stage-dependent heating rate of GPSL for general smearing profile and then profiling following the spread of reference 23. We investigate which profiles for fixed smearing lengths RC and RG minimize the heating rate. The general solution to this problem is a stage-dependent, but we identify two classes of relevant physical situations in which we can identify state-independent answers. The first class consists of objects with dimensions much smaller than RC and RG, but whose distances among each other is much higher than RC and RG. In this case, we find that the optimal profiles are Gaussian profile for the measurement part and the radial increasing distribution with compact support for the gravitational feedback part. See figure 3. Remarkably, allowing different smearing can reduce the gravitationally induced heating rate by more than 60 orders of magnitude already when Rg is equal to 10 Rc, while the heating rate induced by the measurement part remains the same. The second class consists of macroscopic objects much larger than Rc and Rg, whose mass density varies on length scales much larger than RC and RG, and whose particle density is high enough to contain many particles in any ball of radius RC and RG within the object. In this case, the two optimal profiles are independent of each other. The optimal profile for the measurement part is a radial decreasing distribution with compact support, while the optimal profile for the feedback part is constant distribution with spherical finite support. Cosmological considerations lead us to claim that the first class of situation is the most relevant to decide which smearing distributions should be chosen for the GPSL model. Now I want to have a review on figure 1. Pictorial representation of GPS mechanism. Two quantum objects, green as a G and blue as a B, are both in a superposition of two states, left L and right R. Unit until there is a collapse event, the two objects don't interact gravitationally. Then, in this example, the blue object spontaneously localizes with a flash located at X flash associated to the flash. The unitary operation UAGX flash attracts all masses toward the collapse center. So this green, we have the two quantum objects, green objects and blue objects, and suddenly this blue object spontaneously localized the flash object, and we have a gravitational feedback from the other sections that drag the other quantum particles and objects to inside itself. Finally, we compare the model's predictions with observations. We estimate the GPSL induced spontaneous heating in neutron stars and compare the theoretical predictions with astronomical data to derive both upper and lower bounds on the model's parameters, similarly to what was done in reference 24 and 25 for the GCSL and DP spontaneous collapse model in references 26 and 27. The lower boundaries are particularly significant. Unlike theoretical lower bounds based on the assumptions about collapse efficacy, these rest directly on observational data. In fact, as we will see, given the collapse rate lambda, two terms will contribute to the spontaneous heating, one are proportional to the lambda and originating in the collapse mechanisms, and one proportional to the lambda to the power of -1, and due to the gravitational feedback. In general, collapse models without gravitational feedback lack the latter terms, so that lower bounds to lambda can only be set by requiring a certain effect of the collapse mechanism. Studying astrophysical heating complements existing laboratory-based constraints on hybrid models by probing a different physical regime, extreme mass densities inaccessible to the terrestrial experiments. The paper is structured as follows. In sections 2, we summarize the GPSL model focusing on its phenomenologically relevant equations. In section 3, we derive the state-dependent heating rate formula and find the state-independent optimal distributions for minimizing the heating rate in the relevant physical regime. We also discuss why on a cosmological scale isolated particles give the highest contribution to the total heating rate of GPSL and why. Therefore, this is the situation one should consider with the aim of minimizing the deviations induced by GPSL with respect to standard quantum mechanisms. In section 4, we estimate the heating rate for neutron stars and compare the theoretical estimations with astronomical data to put upper and lower bounds on the GPSL model parameters. Then in section 5, we merge these bounds with stronger upper bounds coming from just the measurement part in the reference 28 of the dynamics. Finally, we discuss the results in sections 6. Now I want to go through another section, sections 2, the GPSL model. The model investigated in reference 8 is based on the previously exposed idea in reference 21, which we now summarize. We first deal with a non-relativistic spontaneous collapse modeled in references 26, 27, and 31. The Poissonian spontaneous localization (PSL) model. In this model, the probability density for collapse to occur at a space-time point Tx is proportional to the expectation value of the smear mass density operator at that time and in that spatial location. We denote the center of such collapses by flashes following standard terminology in the foundations of physics. The classical gravitational field is then sourced by these flashes. This is each of these flashes sources a gravitational pulse that acts back on the already collapsed matter wave function. Adding these gravitational feedback mechanisms to PSL or Poissonian spontaneous localizations model gives the hybrid classical quantum Newtonian gravitational model that we denoted by the gravitational PSL GPSL. In this work, we only need two resulting the effective dynamics, so we restrict ourselves to the minimum ingredients required later for the analysis of their heating rate. Detailed derivations and further discussions can be found in reference 8 and 21. The empirical predictions of GPSL are encoded in the master equations. Derivative of the density T based on the time is equal to -I divided by h brackets uh, Enthalpy rho or as a density T plus the L GPSL rho T. In the above equations, H is the standard Hamiltonian of the system without the gravitational part. Micro RCX is the smeared mass density operator. Micro RCX is almost equal to GRC multiplied by microporine. X lambda is the collapse rate. M0 is the proton mass, and UGX is equal to exponential minus I divided by lambda H. Px is a unitary operator responsible for the gravitational dynamics, where Px is equal to minus m0g integral third derivative y absolute x minus y micro rg, with the g being the gravitational constant, and micro rgx is equal to grg multiplied by micro Purine is the smear mass density distribution. The unitary operators UGX is the void associated to each flash the gravitational impulse feedback. The PSL model can be reobtained from the GPSL model by setting the G is equal to 0 so that UGX becomes the identity operator. In this case, we will write the LAPSL bracket rho T instead of the LAGPSL absolute rho T. Notice that in the constraint to reference 8, we are here accounting for the possibility that the smearing appearing inside Px is different from that due to the measurement part of the dynamics. The two smearing distributions are characterized respectively by length scales RC and RG in the sense that their variances amount to RC to the power of 2 and RG to the power of 2 respectively. For a system of n particles where micro sigma x is equal to sigma L, our boundary is j, mj, g sigma, and x minus q print j, and m is equal to sigma lower boundary is j, mj. The master equation becomes as equations 3 and 4 and 5. Now the next section is hitting rate of the PSL and GPSL models. Both the PSL and GPSL model entails a spontaneous increase of the total energy due to the modifications with respect to the standard quantum mechanics. Here we find the relevant formulas for this heating rate. We start from the PSL case and then investigate the GPSL case. Following reference 23, we will discuss the Smith distribution that minimize the spontaneous heating rate. Unlike models based on the weekly continuous monitoring based on the reference 23, however, for both PSL and GPSL, the heating rate is not simply proportional to a fixed state independent function of the smearing distributions. Instead, it depends on the spatial distribution of the particles. Therefore, as we will show, there is no state-independent optimal profile to choose. We will identify two relevant physical regimes in which it is possible to find state-independent analytical solutions. Heating rate of the PSL model. Let us consider a system of n particles governed by the Hamiltonian. Hamiltonian is equal to sigma L, our boundary j is equal to 1, the upper boundary is n, p j to the power of 2 divided by 2 m j plus v, and the parenthesis qi until qn, where mj is a j particles mass, pj is a momentum operator, and q per j is a position operator. Using equation 1 with PSL instead of LGPSL, for example, setting G is equal to 0, straightforward calculations lead to the following expressions for the heating rate ET as the equation 6, with the delta J denoting the gradient with respect to the J particle position. Notice that the energy increase only affects the kinetic energy of the particles because VQI until Qn computes with additional dissipator introduced by the PSL model. If the system is composed of a single particle, the above quantity becomes state independent. where IF is also called the Dirichlet energy of the function fa based on the reference to 32. In this case, the PSL model exactly reduces to the GRW model, and the smearing distribution minimizing the spontaneous heating is the Gaussian distribution, which gives the IA square root GRC is equal to 3 divided by 8. RC to the power of minus 2 is almost equal to 0.375 multiplied by RC to the power of minus 2. As anticipated, the heating rate of PSL is not in general independent of the quantum state. However, we can single out two important limit cases. The first is all particles or clusters with a radius much smaller than RC. The system behaves as a single particle of mass m is equal to sigma j mj. All particles are much further apart than RC from each other so that each one undergoes an independent collapse dynamics. Then we get that the case 1 we have an ion GRC P rho T tends to IA square root GRC, and case 2 IL GRC rho T tends to NI square root GRC. In both these limiting cases, the minimization problem becomes the same as in the GRW model, and the Gaussian smearing becomes optimal. However, this is not true in general, as we show numerically with a two-particle counterexample in Appendix A. Moreover, it is quite easy to prove, see Appendix B, that in GRC ROT is less than the NI square root GRC. Ideally, one would also like to prove that the IN GRC ROT is much more greater than the I square root GRC, as this would imply that the heating rate of a collection of particles is always higher than or equal to that of a single particle. However, we managed to prove C appendix B that CF is equation 7, so that the lambda h to the power of 2 divided by m0 icon GRC rho T gives the kinetic energy increase to center of mass of the system due to the spontaneous localization mechanism. Then the first inequality of equation 11 tells us that the total heating rate is always higher than that of the center of mass. Indeed, INGRC rho T also takes into account in the internal heating. The second inequality instead shows that the center of the mass heating is attenuated by the system containing more than one particle or length larger than RC. In fact, R square root GRC is the isolated single particle heating rate, and I central mass GRC rate reduces to it when all particles are clustered within a spatial region characterized by a length much smaller than RC. When considering a macroscopic body, central mass geoceanity shows that the central mass diffusion depends on the variation of its mass density. This qualitatively agrees with the approximate formulas found in reference 28 for a rigid body of constant density, where R is the surface area of rigid body and V is its volume. Another relevant situation consists of considering an object in which each particle is on average localized on the scale much smaller than RC. The macroscopic density micro X of the object varies on a scale much larger than the RC, and the particle density within the object is high enough that in any ball of the radius RC there are many particles. In this case, we can estimate the heating rate as follows. We first write the equation 7. Since we assume that every particle is localized on a length scale much smaller than the RC, we can make the substitution GRC QAJ minus X tends to GRC QAJ minus X, where QAJ is the average position of the J particle. Then using the assumption that For any x, many particles appreciably contribute to the evaluation of the microperiod RC. We can make the substitution 1 divided by microperiod RC is equal to 1 divided by micro RC because we can neglect the fluctuations in microperiod RC. Finally, for all x in the bulk away from the surface, we can make the substitution 1 divided by micro RC is almost equal to 1 divided by micro m. To sum up, the above quantity can be estimated by making the substitution. In doing so, we identify the microperimeter CX with micro mx, which only works well in the inside of the macroscopic object but doesn't work near on the RC length scale, the surface of it. Moreover, while microperimeter RCX is never zero, micro MX is zero outside of the macroscopic boundaries of the macroscopic object. Therefore, the above approximation should be used only when X belongs to Vm, where Vm denotes the spatial volume occupied by the macroscopic object. Then one can substitute the summation in equation 14 with an integration over the classical mass density between the object's volume Vm and exploiting again the fact that micro mx varies over scales much larger than RC, while delta absolute delta G RC Qj minus x to the power of 2 decays over this length scale. One gets these equations in 16, where we define the state independent quantity IRC is equal to 1 divided by 8 and calculate the third derivative of x absolute delta GRC x to the power of 2 to extract micro m x from the second or integral. We assume that it varies over length much higher than the RC, which cannot be true at the boundary of the macroscopic body. Thus, there should be boundary corrections to the above formula that takes into account this fact. However, the percentage of the macroscopic volume over which the approximation we made don't work is roughly given by the RCO divided by Vm, where R is the surface area of the macroscopic body. Indeed, for a true macroscopic body, this will be much smaller than 1. There are some important facts to notice about the formula. On GRC purity is almost equal to Vm IRC, which we are now going to discuss. The heating rate is independent of the mass density profile of the object under consideration. The heating rate is proportional to the volume Vm of the macroscopic object, meaning that the temperature increase rate of the object of constant density is actually dependent of their volume or shape. In fact, denoting by 3 an object's temperature, by CT is heat capacity, and by ST is equal to CT divided by Vm its volumetric heat capacity, one that has these equations based on the 70. So thank you so much for watching my tutorial video until the end. Today is the 19th day of July 2020. 6 times 2:22 a.m. based on the Tehran